got his PhD in mechanical engineering at Purdue University, and he lives and works outside of Fort Wayne, Indiana, for MathWorks, and he's going to tell us what he does. Great.
Sounds great.
He's worked there since
2013, so about 23 years. So a little while. It's probably some older than maybe some people. So anyway, so today I want to talk about AI workflows and modern control system and deployment. So the main objectives of my talk is maybe to give a little bit more industry perspective on AI and engineered systems, but not maybe all the technical details that you maybe get with other presentations here going deep into theorems. I want to talk about some of the trends, talk about successes, some of the user stories that we have with some of our customers of how they're applying AI into their systems, and then some of the challenges. And so while being from MathWorks, I'll talk a lot about Simulink and MATLAB in terms of how customers have used our tools. You know, there's a plethora of tools out there that you can apply to engineered systems. So I'll talk a little bit about, give an introduction, talk a little about model-based design and regulations, and then go into applications of AI and engineering. So trend number one, there's a lot of shift from general purpose AI to solving very specific domain problems from predictive maintenance, visual inspection, et cetera. In this talk, we'll be focused on two topics that are related to control systems, which is virtual sensing and data-driven control systems. Another trend is AI is being used to enhance various aspects of the control system. So if we look at here, we have planning, control, perception, and system modeling. We've seen AI applied through system identification and reduced order modeling. We see a lot of virtual sensing being achieved through AI that was difficult in the past, and also using AI for planning and control. Another trend is the need to deploy to embedded devices. We all see LLMs running out natively in the cloud or these large compute systems with high-powered GPUs. When we get into industry and need to deploy these to embedded devices, we're no longer to look at, we don't have the power requirements or the computational requirements to house large models or execute large models. So when we look at embedded devices, we're looking at how do we shrink down these AI models into a small number of parameters that can run real-time inference. So we need to be able to run real-time in the process. So, we have limited memory, limited performance, limited power consumption. So how do we address those things? We still need to maintain good throughput for the inference of the model. We need to minimize its footprint. And also, as we minimize the footprint and memory and performance, we want to make sure we don't reduce the accuracy that much. So there's a lot of things that go into compressing a neural network. And we'll talk a little bit how we go about that. A third trend is increased focus in regulations. We see different specs becoming available. So the ISO passed 8800 that's been released recently, which is automotive related to using safety with artificial intelligence. There's the aerospace ARP 6983 standard. This is work in progress now, but it's supposed to come out later this summer or fall. And this is standards with respect to aerospace. And then there's also other things in medical devices with enabling how do you certify medical devices. So a lot of these regulations are focused on how AI systems are being certified. A large number of these are around perception more than control. Control ones are being added, but a large number of these you'll see in these certifications are related to the perception side more than the control side. And so that's one of the interesting problems is on the control side, which is related to this community. And the other thing we're seeing is the if you look at this as a technology readiness, this is a thing that NASA uses. You have the academic on one side, you have industry on the other side. And how do you get the research to the industry, the applied application of these things in research? And we're actually starting to see a progress of this moving. Some of the challenges that are being addressed is the verification validation pieces. One of the challenges is the lack of expertise of people in the industry applying some of these new techniques with AI. When you start using AI, there's a lot of hyperparameters to tune. How do you do simulation in the real world? And also there's a lack of track record, right? So like in aerospace, gain schedule PID control has a strong track record in terms of certifying those types of controllers and them being reliable. AI doesn't have that track record of reliability. So, but so these are being addressed, and we're seeing more and more adoption and production from industry. So I want to talk first about how does AI change model-based design? So model-based design is one of the common ways that people and industry attack problems. So model-based design is using a model-centric approach. You have a model that you do your simulation, analysis, design, testing, et cetera. It includes automation so that when you go to coding and verification, those types of steps can be done automatically. And so this makes the model-centric viewpoint for doing design. It saves costs in terms of trying different techniques before you actually go build a product. And this is being used in industry across all different types of industry applications. A typical design process is the design V or the V cycle process, which you might see in one of your classes. So you start with your system or subsystem requirements, and you start decomposing that into your system level design, from high level design, detailed design, where you might be doing prototyping. Then you go into code generation, and then once you do code generation, you start doing your validation and verification, doing unit and subsystem testing, integration testing, which might be software in the loop, processor in the loop, or hardware in the loop. And so this is a typical design process that many people in industry follow for tracing your requirements to the various testing and certification. However, when we start looking at AI design, there's additional components that we need to address. One of the components is data generation and preparation. How was your data collected? How is your data pre-processed? Did you do augmentation? What are the distributions of your data? Do you have independent training data or for independent data for training and validation, et cetera? Another topic is your model structure and your learning algorithm, right? So is my learning algorithm stable? Do I know that it converges to a solution? Can I guarantee you that? Is my model structure appropriate? Can I guarantee you that it doesn't violate some bounds, maybe a Lipschitz bound or something in continuity? And then AI verification, that also goes into analyzing robustness, generalization. Does my system generalize outside of its distribution? What kind of coverage? Can I explain what the AI system is doing? Then simulation and testing, there's a lot of new requirements in terms of verification and validation. And as I mentioned, deployment becomes an issue with respect to size and throughput. So we start looking at model compression and aspects of the deployment. So to address this, different organizations are coming up with different sort of design V cycles. So here is a W-shaped cycle. It's kind of similar to the V cycle in terms of you start with your system requirements. However, you start having the aspects that I mentioned on the previous slide, where you have data management, the learning process, the model training, learning process verification, model implementation, and verification up. So it's similar to the design V aspect, but adds these extra steps that are specific to the AI system. And you can superimpose these two so that you can have this pretty similar workflow for your non-AI components as with your AI components. So this design W has been one of the more popular ones. There are other organizations that have similar type of augmentations to design process. So there's this modified V diagram, as well as this ISO 880 or 8800, where they have similar different versions, but they're trying to capture that same type of process that's different with respect to AI in your system or machine learning. So AI is they're starting to become standards at every level of government. You'll see at the lowest level, you see different countries creating AI acts, even individual states creating AI acts that may have to be satisfied by a particular customer. There's some broader standards with ISO and NIST. There's some industry-specific standards, which I talked about, like the ARP 693 and the ISO 8800, as well as some other ones. And then we get up to the AI verification. These are some of the ones that are maybe more specific to what we look at and look at, where we might have AI verification through formal methods, runtime monitoring, et cetera, If we look at some of these ISO standards here, some are related to the robustness of the neural network. How is the data managed for the quality of, for analytics and machine learning, and ways to classify performance. So there's different standards that are coming out for different applications of AI that are going to be needed to meet in the future. And one of the challenges with some of these higher level regulations, how do you make sure you satisfy all of them? So one of the ways of doing verification is through trying to analyze certain properties of AI systems. So you might have analysis that looks at moneticity of a network. You know, do I guarantee that it always increases or it always decreases? You might have some boundedness for convexity in your network, or you might have some Lipschitz condition or robustness condition on the system. And this is great for analysis, you know, once you design a system and analyze the system, see if it satisfies these conditions. But one of the challenges is how do I enforce this during learning, right? Because I don't want to post-analyze the network and realize I have to retrain it because it didn't satisfy certain conditions. So constrained learning goes into sort of the learning assurance aspect of the design W in terms of, can I guarantee during learning that I satisfy some certain condition that I need for certification? So in a typical constrained learning process is going through a loop where you do a learning step. If the condition is satisfied, you leverage those parameters. If your constraint is violated, you might do some sort of projection through like a LMI or SDP, which can be expensive and may not scale well. So this can be an expensive step in enforcing a behavior during learning. But the key is that you can enforce these behaviors during learning, which gives you a certain amount of certification that I can say, you know, this learning process will satisfy this condition. And there's a lot of work happening in this area. So, you know, there's different groups are doing various things with deep learning, passivity, stability margins. Pete Seiler's paper's up there at the top. There's a lot of people are doing various things in various areas, which are contributing to how do we verify these systems, closed loop stability or stability analysis or these other properties, as well as how do we enforce them during learning. Another part of formal verification is out of distribution detection. AI models are usually learned on a particular distribution of data. So what happens when your data doesn't fit that distribution? Does your model generalize to it? And typically, people in industry use detectors. So if their data is out of distribution, they might say, hey, I need to look at this, take a look at this data, or I need to perform a different action. It's sort of maybe like if you're doing model predictive control and you get an infeasible solution, what do you do? What do you do with that answer? Oops. Explainability is a big thing. For like classification, people use such things as saliency maps. This kind of highlights the region that's gaining attention from the neural network when it makes its decision. So if you're trying to debug or explain why is the answer you're getting from a particular neural network, you can use these type of techniques to improve explainability. And so there's lots of things that are going on in the verification world. Some of the tools that are used for verification, MathWorks has a deep learning toolbox, verification toolbox library. There's also a very popular open source package called Alpha Beta Crown, which is being used. So these are two packages that are available out there to leverage and have some of the features to verify some of these concepts. And actually MathWorks is going to have a MATLAB interface into Alpha Beta Crown in the upcoming release. But this is a big area of research in various aspects. And I think this is one of the biggest challenges that customers or our customers in industry have in terms of adoption of proving these guarantees in these control systems. We do have an example that shows going through certification of DALD level of assurance for the DO178C compliant. So this is a runway classifier system. So this is using camera vision to detect runway signs. And so this is one of the examples that shows this entire workflow of going from the requirements through all the design processes to show the certification validation at a design assurance level D. So design assurance level D just means there's different levels of assurances in an arrow, which is like A means likely death, B is likely injury, serious injury, down to E, which means if it fails, it doesn't matter. But so D is like one level of, if it fails, it's annoying, but maybe not critical. So it depends on what type of systems you're looking at, require a different level of assurance. Yeah.
Usually the aerospace software requirements they're like process oriented. You do these things, there's not an attached probability that the software is going to fail. Like the hardware, there's usually like fault tree, attached probabilities that they're going to fail. But these AI embedded, like enabled systems, they all have probabilities of failure. That's even built into the training. So how do they like tie that to traditional software certification processes, which generally don't try to think about like, oh, there's a probability of there's a bug. They don't certify in that way.
Yeah, so I'm not very going to answer that question that deep level of detail, but I do know that they're going through these so MathWorks participates as part of that AARP or ARP standard, and so we're looking at how do you certify these features, and part of it is some of these tools and verification, like showing like the robustness, right? So how much adversarial attack could I have, or adversarial perturbation could I have on an image there before that classifier, that runway sign becomes invalid or whatever. So there's robustness conditions like that on the classification aspect and others that are being used in terms of setting this level of certification. I only kind of know things at the high level, not at the deeper level, but I can put you in contact with somebody with the deeper. But anyway, so this is one of the examples going towards like how AI is affecting design and what are the types of things that need to be done in terms of certification. So next I'll jump into control. So if we look at the first part of system identification, reduced order modeling, we'll talk about how AI is impacting that. So system identification and reduced order modeling is very important. It can improve system level simulation. So if you're doing some analysis study, you can actually speed up simulations by creating these surrogate models to achieve your designs faster. Oftentimes, if you're doing hardware in a loop, it might be hard to get your simulation run fast enough in real time to do hardware in loop testing. I'll talk a little bit about that. Having a more simplified model and control design, or maybe a model that's differentiable. Virtual sensing is a very popular thing, especially with AI models, which I'll talk a little bit more in, and digital twin. So there's a lot of use cases for these surrogate models. So sometimes people distinguish between system identification as model derived from a physical system and reduced order modeling as driving models from an existing model. I know it's a kind of semantic difference, but some people differentiate where you're starting from a physical system or an existing model in terms of it's called reduced order model or system identification. And the goal here is to create an AI model that runs fast and accurate over the operating region, and maybe a neural state space model such as on the left, which is a state space model, or you might have a more traditional IO model on the right here, which may have a recurrent neural networks in it. So the goal here is to create models that are surrogate models that benefit in different ways. So one example is in hardware in the loop, as I mentioned. Here we have a model that's a finite element model. When you run this in code simulation, it takes about 30 seconds per time step, right? So there's no way you can run that in a hardware in the loop type testing, right? So quickly here, you can use reduced order modeling, generate data, learn a neural network for it, such as a neural space system, and then you can then use that into generate code for your real-time computer with your target platform and do software or do hardware in the loop testing. So this is a very popular method. The great thing about this is it isn't really safety critical, right? You're using it as an internal design process for the system. As we look at models, people are looking at how can I incorporate more domain knowledge into the system? And there's a couple ways of doing that. One is to use a nominal model and using neural network to model the residual. So you may have a linear system or you may have some dynamic systems that you model that as best you can, and then you use a neural network to model all the remaining error terms. So that's a common practice in terms of putting your domain knowledge or physics, making it physics informed. Another way to incorporate your domain knowledge, like I mentioned before, is to do constrained learning or put these constraints. They could be some examples, like I mentioned, monotonicity and robustness, or you might have some domain equations such as the heat equation you're trying to satisfy. So you might make sure that your neural network satisfies this equation. And this can be either done through constrained learning, where you actually do a projection after each learning, or you can incorporate it in a regularization as part of the loss. The downside with the regularization piece, you can think of it as encouraging the model to learn that behavior, but doesn't guarantee it. Where when you do constrained learning, you're projecting, so you're forcing the solution to be in a valid space. So one way to think about it, I met with several people that were doing battery stuff today. So if you think of battery charging, if we wanted to do an AI model, we might say, have a requirement, right? So if I'm charging the battery, I expect the state of charge to always be increasing, right? If I'm discharging the battery, I always expect the battery to be state of charge to be decreasing, right? So I could enforce that monoticity on the model to guarantee that at least I'm getting some physical behavior that's meaningful. I'm not getting models that are increasing the state of charge as I'm discharging the battery, et cetera. So there's different ways of introducing the physical information into the modeling, but this is a pretty simple example to kind of describe the concept, which is being used by many people in industry. So a couple examples, we have a couple of user stories from Subaru and Cummins. I'll just go over the Subaru one. So Subaru created an AI model for their system, and it actually decreased the time to run the calculations by 99%. That's a huge amount for them from this model. And so they use their models in analysis and designing their problem and analyzing the solutions to their problem. So by speeding up your model by 99%, they can run that many more simulations faster, thus decreasing their time to do their analysis. So, there's a lot of power in generating these AI models to facilitate work. The next part, I know I kind of jumped through topics pretty fast, but I'm just trying to give an overview of sort of how industries are using these various aspects. So the next part, I'll talk a little bit more control-centric.
Yeah.
Yeah. Yeah.
Is there a verification or validation process of there, or do you just do like some test train and?
Most of it is test train. I mean, I think that's part of the formal verification. We're trying to do, you can do stuff with constrained learning, like when we did the battery charging, we did constrained learning with that monoticity thing as part of the learning routine. So it'd do a stop and then it would project. And so you guarantee certain behaviors. We're doing stuff like that with Lipschitz and stuff like that. We're looking to do more stuff with other like conic sectors, like, you can think of small gain, passivity, IQC, to try to enforce certain solutions or certain behavior in there. I see a lot of stuff being done with regularization to do it, which is enforces it. There is also additional work. Ian Manchester does some work where they do a transformation, and then that transformation is supposed to allow it to do unconstrained learning, but while in the transformation maintains whatever the constraints, like an IQC constraint. So there's research in various different areas that I think will solve those problems, but some people do the regularization and then the verification, like the analysis afterwards, and then you don't always guarantee that you satisfy the conditions. And doing constrained learning with projection can be expensive because sometimes it doesn't scale well, and the projection step can be expensive. So there's trade-offs.
Satisfying constraints, the behavior can deviate in some other needs.
Oh, yeah. So, I mean, you might look at error, like I mentioned, you might have some sort of equation that so you might enforce like a heat equation or some physical constraint between different variables, that behavior, or I can have the partial of whatever, and if I can, with a neural network, I can do the auto diff of this partial with respect to that minus this, and actually use that as a regularization term to try to enforce that behavior. And then when you plot it, you can also look at how well is this equation satisfied while you roll out models. So you can also look at how well is it satisfying that constraint that you're trying to impose. That answer your question or enough? Well, that's the big area is the verification validation. And I think, one of the big takeaways from this is that's what's preventing some of the adoption in industry is how do I make these things? And some of the certifications are trying to address what needs to be done to say it's acceptable.
Yeah, may I ask a follow-up on
Yeah.
that? There's a bunch of different industries, actually, I'm not gonna.
Okay.
A bunch of different industries that you've kind of mentioned, and they have different levels of criticality. If I'm working on a washing machine and it's AI enabled, kind of doesn't matter
Yeah.
if the washing machine doesn't flood my house or something.
Or hurt somebody or.
Yeah, and if it's an airplane, that's a different.
Yeah, yeah.
And even on airplane, you talk about, D, like that's like the lowest level of criticality, like,
E is, but yeah, D is pretty low. Yeah,
okay.
yeah, but yeah,
But if it's like level A, then it's a different story.
yeah, it's a completely different story.
Crash plane, hundreds of people.
Yeah.
So like, as you like interact or your colleagues interact with different companies, how do they view this? Do they view this as like try to prove it out? I mean, this is what I envision they're doing. Prove it out in the very lowest levels of criticality, gain confidence, and because again, none of these things are going to work with 100% probability. But even flight controls, we don't design to be 100% safe. We prove it to be a certain probability of safety.
Yeah.
So
I think those are going to come into play. Like in automotive, sometimes they say, well, I want to be 100% safe, but should the safety level be at the level of a normal operation of humans or what level better? I think part of it is like we work with a lot of customers in terms of we have deep engagements with them and we help them get to the level that they want. I mean, some of this stuff is in R&D, like you mentioned, a lot of the applications are not necessarily safety critical or like with virtual sensors, they can be redundant sensors. So you can have an actual sensor and then have a virtual sensor, so it's AI, which could be used for fault detection or, if this sensor went bad or whatever as a redundancy, or as a supplemental measurement for a control system, which isn't necessarily safety critical, but can be leveraged to enhance performance or do additional things. So it's really up to the industry, and like the ARP standard, they're having a collision avoidance system in that as well, which I'm assuming is going to be a higher level certification level. But I think at the beginning, one thing I want to mention is a lot of these certifications are heavy on the perception side versus the control side. So that's where there's a little bit of difference in terms of, I wouldn't say safety critical, but some of them are more on the perception side than the control side. So I think the control ones are going to be the much more harder to.
Is that because of, I can envision there's almost no other way to do a lot of the perception, like things in autonomous driving and so on, without having AI-enabled components. Whereas we have solutions for control.
Yeah.
Was it from the customer's point of view, there's just not a need to do this for control, or we actually in certain applications would have done better if we could have AI-enabled components, but it's the certification is the issue.
Yeah.
Is it the performance or the certification?
I think a lot of customers doing exploration, at least in safety. What can I achieve? So as a benchmark or, a goal. And part of it is also explainability. People are trying to look at, is there other ways to do explainability or coverage? There's a lot of Monte Carlo testing type stuff that goes on. I think it really varies on industry and what the application is and whether or not they're doing it for production or they're doing it for research at the point. And like I said, the specs are continuously evolving. So, we'll see what comes out of the specs. And like I mentioned, there's a lot of research done on how do we verify closed loop stability and stuff like that when we start doing these AI models. And I think pulling that research into a scalable way in the industry is going to make the biggest change in adoption for control systems. But there's quite a bit you can benefit from virtual sensors. Like I might be able to get a NOx measurement that I can't afford to put on a car, but I can get that NOx measurement and then utilize that in my control system. So we had a project with Yanmar who does diesel engines for like excavators and stuff, and they actually used reinforcement learning to do calibration to reduce their NOx emission. And they had hand calibrators, but the time it took to do hand calibration, they still hand calibrate after the initial thing of reinforcement learning currently, but they able to get to the solution in like a fifth of the time. So there's a lot of, I think, advantages of doing things where you might be able to leverage that information in a control system, but that you wouldn't other have from a sensor. So what is a virtual sensor? So a virtual sensor is just something that mimics a physical sensor using other data and estimates that you measure. And why would you want to use this? It could be expensive, like putting a NOx sensor on a vehicle is expensive, but if I can get that information from other measurements, it's great. Sometimes sensors can be unreliable, or they might have a time constant that's not suitable for the situation. Virtual sensors, they don't degrade over time other than the measurements they're on. If you're requiring redundancy, like I mentioned, a virtual sensor might be the way to go to, instead of putting another sensor in there, to have your redundancy through a virtual sensor. And in the past, virtual sensors would be done by manually engineering features that you would use to try to estimate that measurement. And so one thing that deep learning or AI does is tries to extract what are those features that I need to make this measurement, right? And so that was one of the challenging part, and deep learning allows those features to evolve through the learning process. So we have several user stories with virtual sensors. Like Mercedes used it for measuring their engine piston pressure. They initially did their deep learning in Keras to do their model, deep learning model, and then for integration and deployment, they brought it into Simulink, did fixed point design to reduce the size of the model and put it on their target hardware. Coca-Cola had an interesting one. They needed a pressure sensor for their system for diagnostics, and so they're looking at refitting 10,000 machines to put this sensor on there, but then they're able to figure out that they could actually estimate this measurement from other measurements. So all they had to do is redeploy some code to their code processor, and so they're able to leverage a virtual sensor, which would have been costly to implement in a physical state with their existing machine. So virtual sensors are a nice way to achieve various outcomes and different applications. Yes.
So very quick question. So if you, regarding this virtual sensor, if you consider your measurement module is Y equals to GX or GXU, so this virtual sensor is something like G inverse.
I wouldn't say it's G inverse. It's basically just learning. You have your set of measurements. You have a network, right? And you have your measurement that you're trying to measure, and you're just doing supervised learning to try to figure out what is the best fit for that, right? So features should come out of your measurements. You might see some measurements may not contribute much. You might see that if you do what's it called? Like there's a thing called node coverage where you can look at your network and you can see some nodes that maybe never actually exist, right? Or never get fired, right? So those can be removed from the model, or maybe that doesn't have an influence on it. Or you can look at the sensitivities through the gradients, but it is usually the features and stuff outcome is just a model fitting approach. It's not actually trying to compute an inverse. It's just trying to take this data and determine.
Yeah, the point is you cannot measure it in real time and
So the actual measurement, usually either comes from simulation, or they might have a setup where they do put, let's say, a NOx sensor in there that they wouldn't actually have in the vehicle. So they actually have data with a particular sensor on the actual, like a experimental setup. And then they take that data and learn.
Yeah.
And learn the process. So yeah, you definitely need like the label data of the solution. Okay, so let's talk about next control. So imitation learning. People try to do this with, I have an expert operator. Can I replicate his behavior, his or her behavior? And using imitation learning, the downside with this is a lot of times when you have data from an expert operator, they never operate in bad regions. You know, they're not driving off the road or doing bad things. So a lot of times when people try to do this, they actually, you know, it works well when you're in a good situation. But if you go into a bad situation, that the operators, the data from the operator is never seen. A lot of times you can run into issues. So a lot of it's about what data that you put into the system. Other people have looked at trying to improve the throughput of model predictive control through imitation learning. So basically, model predictive control solves either a QP or a nonlinear programming program at each optimization at each step. So if you can learn the solution to the optimization problem, you're going to get an explicit solution to the optimal control problem. And then could I deploy that to get faster throughput and smaller memory footprint on the system? And so that's basically what I just said. So instead of solving the constraint optimization in real time, you do it. And we do have a couple customers that are doing this. We don't have user stories, but we do have some examples. So we did lane keep assist using MPC, and then we basically learned the lane keep policy explicitly using a neural network. And you can see the actuation commands are very similar to the MPC policy, the learn policy was. This is just a couple of the comparisons, but we did extensive Monte Carlo simulations and saw good solutions to this.
A good question. Out of curiosity, if you remember that, because maybe detailed. What was the motivation here? Is the state space so big that NPCs don't go to run fast enough?
We did it with the lane keep assist just as an example, but you might have, if this is nonlinear MPC, it may be expensive to get throughput on the equations. It might actually, sometimes in nonlinear MPC, it's hard coming up with the model and then the gradients for the model. And so if you do a neural state space, or there's a couple things you do, but in here, the goal was to minimize the amount of time. I don't know if I had the numbers on the other slide, but the time it took to execute the neural network policy was much, much lower than it took to execute the nonlinear MPC problem. So you think if you're trying to do higher bandwidth stuff, this would be a solution maybe to overcome some of the challenges of solving the optimization real time. Yeah.
Thank you.
Yeah, and then the other way is to use reduced order modeling to use it in a prediction model here. So as I just mentioned, sometimes when you write nonlinear MPC, you have to come up with the equations for the model, which might be hard if it's nonlinear and very complicated model. You also have to come up with the gradients unless you're going to do numerical perturbations on the gradients for the optimization problem. And so the benefit of coming up with like a neural state space model is you get a nice nonlinear model that can represent your system well, plus it's differentiable, right? So I can use AutoDiff to automatically get the differentiable version of for the gradients for the model to use in optimization for the constraints and the cost and the plant model. So by doing this, it sometimes simplifies the need for writing out manual equations for a complex system as well as computing the gradients. And we have a couple of examples with going that. But the key point here is by doing that, you're reducing the amount of work that's needed on the modeling side and computing the gradients for the MPC controller. The next topic I want to jump to is reinforcement learning. So this is used more on data-driven control and planning. For those that aren't familiar with reinforcement learning, it's basically optimal control. Oftentimes in reinforcement learning, you're trying to maximize the long-term reward versus minimize a cost. But basically, it's still an optimization problem, and constraints are usually handled through putting penalties in the cost and not handled explicitly. So why is reinforcement learning good? It can handle large-scale problems, very nonlinear systems. It can do non-differentiable type optimization. High dimensional space, when you start looking at end-to-end control, which is very hard to verify, but like from images and LiDAR to control actuation, is really hard to use a traditional method handling those types of sizes of observations. So it handles that. It can do hybrid, handle discrete and continuous actions as well. And it's model free. I mean, you need to exercise a system to get data. but it doesn't require any explicit knowledge of the system. And it can do end-to-end solutions. I mean, typically we see customers not doing end-to-end, it's more they have a perception piece and then they use reinforcement learning for the control piece. And we have several user stories related to this. Crohn's used it to improve they make things that make the bottles, like plastic bottles. So the blow molder for that bottle is controlled by a whole bunch of parameters based upon different settings of the environment and so forth. And so they use reinforcement learning to tune that. Let me just go to the individual pages. Max Planck Institute, they use reinforcement learning for measuring gravitational waves. They have a whole bunch of mirrors and optics that they have to do control on. And so they use reinforcement learning to tune the controllers for the mirrors. They also use AI for virtual sensing for the perception. And then they use reinforcement learning for the control of all these mirrors that are used in the gravitational detection. So this is an example where they both use virtual sensing and reinforcement learning in terms of coming up with a more optimized solution for the gravitational detector. As I mentioned, Crohn's use reinforcement learning to improve their thing. And this is another interesting aspect of reinforcement learning. So Lockheed, they're looking at 5G communications. And so they weren't using reinforcement learning to design the system. They're using reinforcement learning to try to find attack vectors, right? So if I attack this system, I went reinforcement learning to try to attack this system and find cases that are not covered by whatever detection systems that they have. And so if you think about it, the system can be complex. You might have different input vectors that change behavior and where you should attack the system. So basically, they're able to use this to identify worst case attack scenarios on this 5G network in their system. So not just for control, but looking at from the adversarial, if you think about robustness, how robust is my system to something, this was being used for an adversarial point of view. So let's see, that one, go over the slide. So a lot of stuff goes into verifiable reinforcement learning. You know, some of the things you might think about is looking at some of your robust control type stuff where I have two systems. I have this water tank model, it's nonlinear, but I know it's passive, right? So if I can guarantee H1 is passive, I can guarantee that the system's closed loop stable, right? So one of the goals is if I do constrained learning for H1 and I can guarantee H1 is passive, I can then guarantee that this closed loop system is stable. So these are some of the things that, as I mentioned early on some of these robustness and other type of conditions like IQC or Lipschitz conditions. Can we enforce these different types of conditions during learning? And then, you know, through our control knowledge, know that the interconnection of these two systems satisfy a certain property. So as an alternative to that, so as I mentioned, there's a lot of people doing research. As an alternative, you know, people, when they look at traditional control systems, like in aerospace, they do gain margin, phase margin, and all these types of things, and they understand them well, and V&V is very established. And then, as I mentioned, V&V is not very established for black box controllers. So some of the things people are doing is looking at topologies, right? So instead of worrying completely about how I satisfy my conditions, you know, I have my black box neural network controller, but I have a traditional controller. So basically, I can run my black box controller if I think I'm getting into a bad situation or need to recover. I can switch to a traditional controller that's satisfied. So this is one way of addressing some of the concerns of maybe I can get more optimal performance, but I always have a fallback that I know is certifiable, right? So it's sort of like putting yourself into an advanced mode that gets more performance, but you can always fall back to the traditional method. Another way is to not replace the controller, but to supplement it, right? So I have a traditional controller loop, and then I learn a supplemental signal from the black box controller that enhances the performance. So there, I'm not trying to learn the entire controller, which sometimes this is more sample efficient than the top piece because you're really just learning a portion of the control, and the traditional controller is already going along good trajectory. So as you look at how do I modify those good trajectories a little bit with the AI controller to get a beneficial system. And of course, if I want to switch back, you know, I just cut off this loop. and now I'm back to my traditional controller. So this is one way of trying to leverage kind of, two worlds, traditional that's certifiable and not. And then another possibility is the assurance mechanism. So these are post-processing the controller. So you have a controller, and then if I don't like what it's doing, I'll post-process it and make it do what I want to do. So, a common thing, if you talk you hear about barrier certificates or control barrier functions, this is like a post-processing technique, or if you want to enforce incremental passivity. But the main goal with the assurance mechanism is I get a control action U, and then I say, well, does it satisfy my requirements, such as a barrier certificate or control the op-and-off function or whatever your constraint is? If it doesn't, then I basically just do a projection, right? I find maybe a QP problem that solves the minimization of the argument of the minimization of how the closest actuation that actually satisfies that constraint, right? And so that's basically what a barrier certificate or barrier control function does. So this is a mechanism of post-processing, and we do have some customers using those. A quick example, this is 3 PID controllers, just having these 3 balls go to different locations. And you can see they actually run through each other on the left. On the right, when there's a barrier certificate, it overrides the control action from the PID controller to satisfy the barrier certificate, and they actually will avoid each other to make sure that they stay in the invariant set. So those are different types of topologies that the customers are using. Instead of just replacing their controllers with black box, they're looking at, can I augment my topology, leverage the advantages I get from AI, but not sacrifice the verification that I get from traditional controllers. The next is going back to AI for deployment. As I mentioned, one of the key things is how do we embed these things on low processors? So a common thing that's being done, there's both memory and throughput, but pruning, projection, and quantization. Pruning is basically when you look at where connections aren't providing much value or they're not adding much to the solution. So pruning refers to removing some of the interconnections between the nodes. Projection you can do where you can collapse things onto a smaller set of nodes. So here we're doing projection to this middle layer to one node, which then further reduces the memory footprint. And then we can do quantization. So looking at quantizing the weight, therefore the weights and biases are smaller, so we get a smaller memory footprint. And so this is a common practice that many of the customers use to put their things on embedded device. And the biggest thing is how do you go from the original thing to the quantized version, but also maintain accuracy? And we have some tools that help you go through that process. And if you look right here, this is one of the common examples. This is a speech recognition, but you can see the original model had 6 times 10 to the 4. The prune model reduced in terms of the number of learnable parameters. Of course, it stayed the same number of size for the quantized because there's the same number of parameters. But then if we look at memory footprint, we can see a great reduction by reducing the number of parameters, and then a large reduction through quantization. So when we want to put these things on smaller devices, we really need to look at the memory footprint that's needed to put these things on devices and evaluate how well the compressed model represents the original model.
Good question.
Yeah.
Out of curiosity, what is the metric that enables the pruning? Is it, assuming that it's some kind of an optimization?
Yeah, there's an optimization. I would have to look it up in the documentation, but there's for both the pruning and projection, there's 4 or 5 different popular methods, and so they've implemented that in our tools to. It basically helps you decide which layers to prune and also evaluate the accuracy. You have different data sets, and it looks at how much the data set accuracy degrades as you do different levels of pruning. Yeah. Sort of an iterative process, but yeah. But it does, there's tools that identify like which layers are good for projection or which layers are good. And sometimes people only quantize portions of their models too, because if you quantize some portions of the model, you might lose too much accuracy, but there's some portions of the model that you can quantize quite a bit.
Yeah, no, I'm asking, I'm asking because, I mean, something that it would be useful in the future in terms, at least in the research. I'm not from that neural network domain, but I would see that, someone will need to reason if I have trained offline through some data, a model, right? A neural network model, but now I'm running my system and I'm collecting new data. Which portions of this model should I adapt online, right? To have better performance. But then the question is that, what is the metric to identify the correct portions and how you do the retraining? And is this the whole procedure scalable in 100 hertz or 1 kilohertz or whatsoever?
Yeah, I mean, most of this is done offline. It's like they do their, deep learning training in MATLAB or PyTorch or whatever. And now I have this model and there's no way I'm going to fit it on a Raspberry Pi or something, or your ECU or whatever. And so what is the process to trim the model to get it to that point?
Yeah, thank you. Well, let's go offline more. Thank you, sir. Thanks so much.
Yeah, so I kind of went through some of these topics quick, but my main goal was to kind of talk about some of the regular, some of the things that you might not see that's industry related, such as some of the governance and regulations, some user stories of how customers or industry people are actually leveraging these models currently in real life production applications, and some of the challenges which were brought up by several people. How do I guarantee these things? And these are some of the parts that, there's a lot of great research out there. And one of the things is, like I mentioned, that technology gap, how do we transfer that stuff into production level type applications from the academic side? So with that, I'll answer any additional questions.
It's great.
Yeah, I'll go ahead. Go ahead.
So you had shown a slide that had out of distribution samples and how the AI model can detect those. So in the field, that means every time I have a new sample, I need to retrain the AI, or do I only need to retrain parts of it?
So typically what they do is it's more of a not necessarily that you need to retrain. I mean, if you're deploying this, you wouldn't be able to retrain immediately, right? It's more about, I don't remember there here. The main thing is I don't necessarily know how my model's going to behave when I'm out of distribution, right? So I may say, I don't know if I want to trust that answer. So, I mean, I always think of it in terms of like MPC. What happens if I do an optimal control problem and it says my solution's infeasible? What do I do? What action do I take, right? So if I have a car that's doing steering with MPC controller and it comes back and says, I couldn't find a solution for you, what do you do? So I think, this is sort of the, hey, I should take a look at this, or how should I react to something that I might not think, this is out of distribution, so I may not trust the result, right? So what mechanism do I put in there to address that? And so I always think of, I'm doing optimization real time and I get an infeasible solution. I need to say, do I keep the current control action? Do I, what do I do? Or do I decrease the speed, or what's the remedy? But I think that's a application dependent thing. But the key thing is this is a common thing that people leverage in terms of validating if they're getting into a situation that's not good.
Do you think you could go to slide 78? I'm sorry for. It's easier if the figures.
Yeah.
You should have asked in the opposite order.
It's like this.
And we'll be around.
Oops.
Yeah, the topology said.
Oops. Oh, I need to build it.
Yeah, this one. So I argue that, the middle topology is not really how it's happening now in the industry, and at least in the self-driving car industry. I think those two boxes are upside down, the black box controller and the traditional. So essentially, the task gets much more complex. then they actually like to use the black box controller, some kind of AI I trained, right? So you can call it end-to-end or whatever, right? But this is what NVIDIA, Tesla, actually many other companies are using now. And they actually use the traditional controller as kind of a backup, right?
Yeah, so I mean, this is sort of a backup situation, right? This is where I'm using the black box controller. And if I don't like what's happening or whatever, then I go back to the traditional controller on the top one.
Yeah, but that diagram doesn't necessarily kind of emphasizes your priority, right? The middle
Oh,
diagram is kind of showing, right?
Yeah.
Yeah,
I see what you're saying. Yeah, I mean, yeah, the middle diagram. So the reason I brought these up is different customers have asked, I want to improve my control performance, but I don't want to have purely a black box controller in my loop, or I want to be able to. And so these are two topologies that we've recommended and people have tried, some people have implemented, that they're looking at how can I improve performance, but I'll still be able to still have the comfort that I have this controller. I mean, some of the stuff that's done in safe learning is also sort of like this too, right? Where they'll do the safe learning on the black box, and if they get in a bad situation, flip. That's usually like in a lab environment. But I'm not saying that these are the best solution. I'm just saying these are alternative topologies to try to address some of the concerns that people have with having a pure black box controller.
Yeah, the other maybe remark on this, so I agree with you that you can start with the traditional and add something on the top. I'm just arguing that many of these companies are actually not doing that, right? For them, we are the backup. And then the other interesting thing is, what is the switch doing? So when do you switch between the two, right? In two ways, right? So one of them is like, okay, how do I formulate these conditions? But the second thing is, black box controllers often use much more data, right? They may go pixel to steering wheel, right? But we live in a state space, right? I mean, that's how we do everything. So it's very non-trivial, at least in the applications I'm working on. It's like how to design this switch. You know, when
So I mean, when to design the switch is an open question, but in terms of switching to the controller, like, we have customers that if they are doing switching controllers, whether it's AI or not, or some other controller, is basically you have uplinks transfer, you're running a tracking signal in like your PID controller, so that when you do switch, you don't have a large discontinuity between them. So there is something like that. But there would be a lot of logic, I think, potentially, like depending on your system, when do I want to revert back, or when do I want to use the new one? It may be, maybe this is a highway controller and that's a urban driving controller type of thing. So I think that's really industry dependent of like when you switch. But the main goal of these pictures were, how can people look at being comfortable in integrating AI stuff with their existing solutions without going pure black box and saying, well, I don't know what's happening. So, but I agree with you. I mean, the different applications I think would look at different topologies different ways.
Just one more question and then.
Oh, sorry. Just a more general question that I have for you, Craig. Can you talk a little bit about the interplay between academia, MathWorks, and the customers themselves? How are ideas generated for these new tools that MathWorks develops? Does the customer come to you and say, hey, we have this problem? Do you turn to academia and say, hey, what ideas, how does that flow work?
Yeah, so there's different avenues. So we have a MATLAB advisory board where we meet with customers every year. It's a big, like, sort of internal conference. We also have a research summit, which we do with, it's kind of similar with professors. So we get a lot of information there. Many of us attend, maybe if you go to the controls conference, you've probably seen me there. So we go to a lot of control conferences, network. We also work with professors we have research collaboration grants that we work with some professors. We hire some professors as consultants on certain topics if it's something that we want to move forward. So there's different avenues that we take. The biggest thing is how are the techniques applicable in a more general case? I mean, sometimes there's really neat research, but it's, tied to a very specifically constrained type of dynamics of the system. But, how do I extend that to something more complicated? I have a Boeing model with 200,000 blocks in it. How do I say that this satisfies this condition of this, control lemma? So I think a lot of it is, where we think we can add value. We think, some of these emerging technologies are, we try to evaluate them, see which things are gaining momentum. We prototype a lot of stuff that we see in academia to try to see, can it extend or how well it extends. But we do rely on professors. We have, agreements with different professors to help us accelerate the technical side where we do more of the implementation details. So it comes from a variety of different pushes. In reinforcement learning, there's like algorithms coming out every week, it feels like sometimes. So, there's things that we've implemented, but we're like, oh, this doesn't really do much better than stochastic actor critic. So why put another method in the toolbox that we're not going to recommend to somebody? So sometimes we prune stuff that we prototyped and stuff, but we're like, well, what is the advantage? I mean, what's the value added proposition, right? Our goal is to make your jobs easier, right? We want you to be more productive, have a platform to run your experiment, your designs, et cetera. So our goal is to make you guys more productive. And so that's how we kind of evaluate what's the value added proposition of a feature.
Okay, well, it's 4:30. Let's thank Craig again. No questions.
Same shit.
Yeah.